And welcome to 4.2, the structure of the nuclear atom, where we're going to be investigating how this atom is put together, at least in part. Now, you may already know that there are three different subatomic particles. Now, the prefix sub simply means below. So when we're talking about subatomic particles, we're talking about particles that are smaller than the atom or below them on the organizational chart, if you will. Now, these particles are protons, which we're going to abbreviate P positive, neutrons, which we're going to abbreviate N0 or NO as the exponent, and then electrons, which we're going to abbreviate E with a minus sign on it. All right, I'm sure you've heard these three subatomic particles before, but now we want to talk about why we believe that these particles exist, or at least in part why we believe these particles exist. Now, the story starts around 1900 with an Englishman by the name of J.J. Thomson. Notice that the spelling of Thomson, there's no P in there. That's an earlier spelling of Thomson, and possibly a British one. And he was doing some experiments using what is called a cathode ray tube. And by the way, cathode ray tubes are what older TVs are using to project their images. Okay, your LCDs and projection and whatnot, those are slightly different. Your LCD, your plasmas, I should say, but the older TVs we're using cathode ray tubes. Now, just a little caveat here. Within the past couple of decades prior to Thomson's experiment, so we're talking about the late 1800s, they were starting to see that atoms were actually emitting particles. As it turns out, part of John Dalton's theory is incorrect, meaning that atoms are the tiniest particles, are the small indestructible particles. They are, in fact, destructible in some way, and so they were actually seeing these particles being emitted, like I said, in the late 1800s, and so they were starting to investigate what these particles were that were being emitted from the atom. And in fact, what these particles are radiation. And for those who go on to take a look at chapter 25 for extra credit, you're going to learn a little bit more about radiation. All right. So anyway, J.J. Thomson was studying one particular type of particle that was being emitted, and he was using what's called a cathode ray tube to study it. Now let me explain how a cathode ray tube works. What you have is a voltage source hooked up to a couple of plates. Here's one plate. Here's another plate. And what happens is when you apply a voltage, it forces particles to be emitted from the plate. And as it turns out, these particles were shooting across, like so. And so he knew that these particles were coming out of the atom. Well, then what he did is he subjected these particles to magnetic plates or electric plates or magnetic fields or electric fields. And so on this bottom side you had a negative plate. On this top side you had a positive plate. And so what he found was when he subjected these particles to this field, they were deflected away from the negative and towards the positive. Well, as you know, like charges repel and opposites attract. So, if the particles are being pushed away from the negative and towards the positive, that means that these particles must be negative. So that's the first bullet point we want to have. Particles repelled by negative plates. Therefore, and I'm going to use a little new notation, it's kind of like a three dots here, bowling ball type of configuration. Therefore, the particles must be negatively charged. And what Thomson called them, he called them corpuscles, but what we now call them are electrons. Those are the negatively charged particles. And then here's a picture of an actual cathode ray tube, and as you put a magnet up to it, you'll see that it's being deflected, in this case, towards this particular pole. So we know that the atom contains negative particles. And since the atom contains negative particles, and it is also known that the atom is neutral, that must mean that something is balancing the charges. So here's John Dalton's marble model. So we'll call this Dalton's marble model. And there we go. Dalton's marble model was neutral. And we won't talk about why they believe it's a sphere. It has to do with, similar to how planets and whatnot are formed in spherical shapes. But he believed it to be a neutral sphere. Now with J.J. Thomson's experiment, we know that there are negative particles in the atom somewhere because we can see them. But to balance the charge, there must be something positive in the atom as well. So since we haven't seen anything that is positive at this point, we're going to simply say that the sphere itself is positive and these negative particles are embedded in and throughout the marble. All right? And he calls this the plum pudding model. Plum pudding, P-U-D-D-I-N-G, plum pudding model of the atom, because it reminded him of a common dessert that was served in England around the turn of the century that was called plum pudding. It'd be considered, it would be kind of a mushy dough type of a thing, which would have been positive, and then raisins are embedded throughout. A better way for us to describe this would be to call it the chocolate chip cookie dough model, because you can almost think of this as a sphere of cookie dough. And so let's go ahead and let's just call that the cookie dough, which would have been positive. The entire thing would have been positive. And then you have the chocolate chips not only on the surface, but all the way throughout the cookie dough. The chocolate chips would be the negative electrons. And so that's how he pictured it, but again, they called it the plum pudding model. So now notice we've advanced the model of the atom from just a sphere that accurately described the knowledge that they had in 1800 to the plum pudding model, which accurately described our understanding of it after J.J. Thomson's cathode ray experiment. Now, J.J. Thomson did earn a Nobel Prize for his experiments and for developing this plum pudding model. Now, as it also turns out, and we're just going to wrap up the podcast with this, they did discover protons, or at least positive particles, being emitted from the atom in 1886, but they really weren't sure how that fit into the actual model of the atom. So, if you're not exactly sure, you can leave that part out as you're developing the model, and then eventually you get a bigger and bigger picture. Neutrons, by the way, were not discovered until 1932 by the guy by the name of James Chadwick. He was working alongside a guy by the name of Ernest Rutherford, who we're going to be talking about in the next podcast. But just to introduce, electrons, protons, and neutrons have been discovered, and were discovered around the turn of the last century. And we're going to be developing the model from the plum pudding model into a closer model, at least one that represents something closer to what we see the atom today. Okay, we'll see you back in just a second with another 4.2 podcast.